In today's lecture in particular, we will be covering some basic concepts of inductive and capacitive circuits and their relationship with the power factor, power triangle, and calculation of power factor will be discussed. Furthermore, we will study the disadvantages and causes of low power factor. And in the end, some methods of its improvement will also be discussed. Okay, so if I take you back to the lecture number 2 on the same course, we studied the concept of calculating the instantaneous power for resistive, inductive, and capacitive circuits. For instance, in case of a resistive load, as you can see from the circuit and from the plot as well, you can see that the voltage and current are in phase. So if this is the phasor, then the voltage and current are in phase, and the power calculated, which is this curve, is positive for both cases during one cycle. So the power stays positive for a resistive load. Now I will quickly move on to an inductive load or inductive circuit. We know that, or consider it as a pure inductive circuit. Okay, we know that the current lags the voltage by 90 degrees. So we know this angle, fine, for a pure inductive case. And you can also see the direction of the phasor. It's in the negative direction. Now, looking at the plot, we can tell the voltage starts ahead. Voltage starts ahead of the current, or the current is lagging, and the value of the power only stays positive for positive values of both current and voltage. So in this section we can see the power remains positive because both current and voltages are positive, and in this case current is positive but the voltage is negative, so that is why the power becomes negative. So, and which also means that the inductor is storing power at this time. When the power is positive, energy is being stored, and when the power is negative, that means the energy is being released during this time. Similarly, in case of a capacitive load or a pure capacitive load, the concept is that the current will lead the voltage. You can see here, for a pure capacitive load, it will lead the voltage by 90 degrees. And from the phasor, you can tell if the voltage is the reference, the current will lead. And in case of, and obviously this is a case of a pure capacitive load. And again, the idea of instantaneous power is the same as of the inductive load, but the only difference is that the current leads the voltage in case of a pure capacitive circuit, and the same will happen that for both positive values of current and voltage, the power will stay positive, and for one negative value it will become negative. And the negative power means the power is being released, and for the positive power, you know that at that time the power is being stored by the load. Okay, so this is just a basic concept which we already studied in the same course. Now, if we talk about power factor, the cosine of angle between the voltage and current in an AC circuit is power factor. As we discussed that from the previous example, let's say if this is an inductive load, then there will be a lag. So this current will be lagging the voltage by some degree phi. Okay, and if we take the cosine, as I said, that cosine of the angle will be the power factor. And we also know that the angle between the current and voltage only appears for reactive load. It can be for inductor and it can be for a capacitor as well, but in case of capacitor it will start leading. The current will start leading for the case of capacitive load. And in the phasor diagram given here, you can see the lag and the lead in case of inductor and capacitor. And we usually try to, what we do is, as an engineer, we usually try to reduce this phase difference, which is the phi. We try to make it close to 0 to reach maximum value of cosine of phi. So for the lower value of cosine of phi, we will get somewhere close to 1. So in short, the power factor is the measurement of how an electric equipment converts the power into useful power. We are going to study the definition of useful power in the coming slides. Now, emphasizing on useful power, let me draw the previous figure one more time. So this was the voltage, reference voltage, and that was the current. So this was the cosine or the x component, and if this was the phi, and this will become the sine component across the y-axis. Okay. The current I can be resolved, as I said, in x and y components. Okay, if I cos phi is in phase with the voltage, then I sin phi is 90 degrees to the I cos phi. Okay, so the x component, which is the I cos phi, is or can be called the useful or the wattful power, and the y component, which is the sin phi, is the reactive component or the wattless component. So active component is I cos phi and reactive component is I sin phi. Okay, understood. So if we reduce the reactive component, which is the I sin phi, okay, let me change the color. If we reduce this component, I sin phi, we will only be left with the I cosine phi. So, and the more the factor of the cosine phi, the more or the improved version of the power factor can be achieved. So in this way, the overall power factor can be achieved by reducing the I sin phi. Okay, here we are again revisiting an old concept from where we previously learned how to calculate the active and reactive powers. We learned that in the previous course even as well, in the previous lecture as well. So if we again consider the previous phasor diagram, which was this, V and I. Okay, so, and if we multiply this, let's say if this is the current vector, if we multiply this with the voltage on this side and the current on the other side, then this will give the power triangle, because this component here will become equal to power. So the I cos factor here and I sin factor here, they are also going to get multiplied by the voltage. So it will give us the reactive power, active power, and apparent power, and overall it will become a power triangle. So again, if I consider this the main diagram, you can see that OA will be the active power and can be represented in watts as active power, and AB, which is this, it will be the reactive power, and is represented by watts, which is this. So that was in watts, this is in var, and this component Vi will be voltage ampere. And this is actually the more real-time representation, or more formal representation of the power in terms of kilo. So this is kilo, K is just the factor kilo. So kilowatt, kilovar, and kilo or kVA. So this is how we represent the power. I'm sure we know that already. Now moving on from the triangle we just considered, there are some other points which can be noted for our information, that apparent power can constitute by taking the square of, okay, let me draw the diagram one more time. So this and this was OA, this was B, okay, and this was angle phi. So what I'm saying is that by taking the square of OA and AB, we can come up with the value of apparent power, which is the square root of the whole expression. So this will become kVA, and as I mentioned that K is just a representation of kilo. So with that, we can, by using the by considering the right angle triangle, we can come up with the value of the apparent power. And now the second point is that the power factor, which is the cos phi, equals to the active power divided by the apparent power. So this is the expression to calculate the cos of phi. And the third point, as I mentioned earlier, in case of an inductive component, we will observe lagging power factor, and also that lagging reactive power, which is constituted, or which is the resultant of the reactive component, is also or is responsible for low power factor. So in short, the inductive component is going to be the factor which is responsible for the low power factor. And if we know that if cos phi is equal to kilowatt by kilo kVA, which is the power factor, and if sine phi equals to k var, which is the reactive power, kilo reactive power, and divided by kilowatt, then kVA, I made a mistake here, kVA, then the tan of this angle phi, which is the phase difference between the voltage and current, is going to be equal to kilowatt divided by kilowatt. And we can also find the value of the phi by taking the tan inverse of this. Now the fourth point states that if we add a capacitor to the same circuit in parallel with the load, then the lagging power factor will get neutralized and the overall power factor can be improved. So for instance, if I give you an example of a capacitive load in a circuit, and let's say this is the reference voltage, and in the case of capacitive load, the current would be leading the voltage by some angle phi. So this is going to be the y component, the sine phi, and of the current, and this is going to be the x component of the current. So what I'm trying to say is that if we just replace the load with a capacitor, the whole power triangle concept can be reversed. Okay, now from according to this point number 5, it can be said that the power factor can be represented in 3 different forms. The first one is cos phi, which is the cosine of the angle between voltage and current. The second one is in the form of resistance and impedance. So resistance divided by the impedance will be the power factor, and the third one is in the form of active power divided by the apparent power. So after the representation of power factor, in this last point, it can be concluded from the power triangle that the reactive power usually does not perform the actual work. It usually flows back and forth in the circuit to create and compensate for the phase difference between the voltage and current. So, as I said, the reactive power can only happen in a circuit because of the reactive component of the circuit. So that reactive component could be an inductor or a capacitor, and depending on the nature of the reactive load, the phase difference will behave. So that is the role of reactive power. Furthermore, the reactive power cannot be measured by a simple wattmeter and usually a digital reactive power meter is used for its measurement. In this slide, we will take an example of a circuit which draws 10 ampere or 10 amperes at 200 volts with the power factor of 0.8. Lagging means it is a inductive load. So in that case, if we calculate the apparent power, it is going to be equal to V times I equals to 200 times 10 equals to 2000 volt ampere. And for the calculation of active power, that is going to be equal to Vi cosine of phi. So it will be 200 times 100 times 0.8, which is the power factor, equals to 1600 watt. And the reactive power will be equal to Vi sine of phi, and phi can be calculated by taking the cos inverse of the power factor. Cos inverse of 0.8 is the angle, so from that angle we take the sine, and sine phi equals to 0.6. so this will become 1200 watt. So this can be put in such a way that the circuit receives apparent power of 2000 volt ampere, and out of which 1600 watt was utilized in the form of real power, and the reactive power, which is 1200 watt, will just be flowing in the circuit without doing any useful work, which means it is just a liability for the source, because it has to create or produce the sine component just for the sake of the angle, because whenever we have a phase difference, there will be some sine factor happening over there in the circuit. So from the previous study, we know that the expression for calculating the useful power in a single and three-phase circuits are these. So this is for the single-phase circuit, this is for the three-phase circuit, and from the expression here, from these two expressions, if you look at the power factor, then we can clearly tell that the load current, which is IL, is inversely proportional to the power factor, which also means that with the lower power factor, the higher current will be drawn by the load. So, and vice versa. So now if a power factor drops below unity, we have studied that the power factor can get reduced because of the reactive component. Now if the power factor drops below unity following could be the disadvantages, and which are large kVA rating of the equipment, greater conductor size, this, and this, which we'll study in the next slide. And there's an interesting point which needs to be noted, that why the electrical machinery is usually rated in kVA. So for that reason is that mostly the generators and transformers, when they are designed or manufactured, they do not have the information of the loads in terms of their power factor, and that is why they are rated in kVA. So otherwise, if the power factor information is given, then this information in the watt can also be given, but that hardly happens or rarely happens, because that transformer or the generating unit will be designed or developed on the demand of a customer, but usually the power factor is not given. So if we talk about the first disadvantage of the lower power factor, the first one is the large rating of the equipment. So from the expression of the power factor, which is this, it means that the kVA rating of the transformer or generator increases for the load with lower power factor. So with low power factor, I mean cos in phi is inversely proportional to this kilowatt ampere, so the overall size of or the rating will be increased. The next is the greater conductor size. In our previous lectures, where we studied the AC and DC transmission and distribution systems, we learned that to transmit fixed power at fixed voltage but at lower power factor, more current will be required, and therefore large conductor size will be required. The next disadvantage which we will study, or which we will observe right now, is due to the low power factor, is the large copper losses. Okay, so as discussed above in the last slide, that with low power factor, load current will be increased, and with the increase in load current, I square R losses will also increase, and that will result in poor efficiency. The next on the list is poor voltage regulation. Okay, we know that for low power factor, the equipment connected would require higher magnitude of current through thicker size of the conductor. Now this will make the voltage drop way before it appears across the load because of the thicker size of the conductor. Therefore, to keep the voltage at the desired value, the voltage regulators will be employed, and that they are going to be employed as an additional hardware or extra equipment. So for proper regulation of the voltage, some extra equipment will be needed, and that will also be costly. The last point is reduced power handling capacity of the system, which means that at low power factor, I sine of phi component, which is a y component, will increase, and that will reduce the percentage utilization of the equipment connected to it, and that also means that we'll be using the power at not full rated, but at some, let's say if a machine is rated for 15 kilowatt, then we probably will be using 10 kilowatt out of it because of the low power factor. So that will reduce the capacity of the system, or the power handling capacity of the system. Now, as discussed and described earlier, power factor is quite significant when it comes to designing a power system, and engineers usually get preloading information, and based on that, generating units and transformers are decided to be connected. And let me tell you another thing, that the practical load which are usually connected to power system, they have power factor of less than 0.8. So and also from economics point of view, the lower the power factor is generally undesirable. I mean, the low power factor is usually undesirable because it can make the things complicated, and also the equipment gets bigger, and with higher rating it will become expensive and inefficient. And if we go much more deeper and we want to know the causes of low power factor, the following could be the reasons. Okay, so the first one is that we know that, and we already discussed so many times, that the majority of the loads in industry and households contain AC motors, which are inductive in nature, which also produce phase shift between the voltage and currents and result in lagging power factor. The power factor of these motor can, they depend on the loading nature first of all, and the loading on the machine as well. So the power factor for these machines could be between 0.2 to 0.9. Okay, the next cause, similarly, it could be for the case of electric lamps. The lamps, not the incandescent lamp, but for the arc type lamps and for the dischargeable lamps, they convert electricity into light, we know that, and they also operate at low power factor, and that can incur high I²R dissipation or losses, and that is also a cause of low power factor. And in terms of these arc lamps, we are going to study this in the forthcoming lectures on illumination studies. And further to that, the last point is that when we have a varying load on a network, which let's say becomes high during the morning and in the evening and stays low during the day. Let's say this is the load curve, and let's say this is from 0 to 24 hours of the day, and during the, let's say from early morning till night, so let's say this is 6 p.m. Sorry, let's say this is from 6 a.m. to 6 a.m. the whole day. As I said, the load, let's say the demand is higher at this point, but stays constant during the day and becomes higher again. So let's say this is the load curve. What I'm trying to say is that if the load is varying, if it has a varying nature, the supply voltage can increase, and this because the load is depending on the current demand. So if the current demand reduces, at that point the voltage can peak up, and because of that, with certain increase in the voltage, there can be some kind of inrush current into the transformer, and that inrush current can increase the magnetization current, and which can also reduce the power factor. Now we will study how the power factor can be improved. We have just learned from the previous slide that majority of the industrial and household loads are inductive in nature, which actually drops the power factor. Now, in order to improve the power factor, a device with leading power factor characteristics can be connected in parallel with the already connected load. In this case, a capacitor can be used to neutralize the lagging reactive component of the load current. And if you look at the figure in the middle, you will be able to locate the connected capacitor, and also on the right hand side the current phasor in the dotted line. This current phasor I dash is the one with reduced phase difference with respect to the voltage, and which eventually can assist in improving the power factor. So if we look more closely into the figure and try to illustrate the mechanism how the power factor is improved with the help of capacitor, we can see that the RL load, which here draws I, current I, this current. Okay, and this load. Okay, and okay, that draws I, and makes a phase angle phi1. This is going to be, okay, let me change the color. Okay, red. Okay, and it makes a angle phi1 with respect to the voltage. I mean, all the way here. The moment when capacitor is connected in parallel, it will draw current IC, which is this, and which leads the source voltage by 90 degrees. So IC will lead the voltage by 90 degrees. But now if we take phasor sum of these two currents by using the parallelogram method, so let's say this is the current IC, sorry, okay, let's say this is IC and that was the current before the capacitor. If we draw the parallelogram, then this I dash is going to be the resultant, and it will have a phase difference of phi 2 with respect to the voltage, and you can see the phi 2 is slightly lesser than phi 1, and which also tells that the cosine of these two angles, cosine of phi 2 will be greater and cosine of phi, compared to cosine of phi 1. That means with the reduced phase difference, with the help of adding a capacitor in parallel, we can increase the power factor. Now, from the illustration in the previous slide, following points are worth noting. First of all, the magnitude of the resultant current I dash is lesser than the previous load current, which I just showed you. If you look here, the magnitude of this phasor is lesser than the I. That means with lesser current there will be lesser losses. Another important thing to notice here is that the active component on the x-axis, which is the I cos phi, remains the same even after the improvement in power factor, because the capacitor can only reduce the phase difference between the y component, which is the I sin phi, which means that I cos phi will be equal to I dash cos phi 2. So what I'm trying to say is that this capacitor will only reduce this angle here, this angle. So this angle will be reduced with the help of capacitor and doesn't have much effect on the x-axis. Okay, and as I just mentioned, that the capacitor will only reduce the I sin phi, which is the y component, to some new angle, which is phi 2. I need to change the color here, which is the phi 2. So the improved reactive component can be calculated as this, which is I dash sin phi 2 equals to this minus the capacitor current. Alright, so from point number 2, where we saw that the active current component stays the same even when the capacitor is introduced, if we multiply both sides with the voltage, this and this, the expression will become the representation of active power, and that can tell that the active power does not change with the addition of capacitor. Similarly, from point 3, where we found out this expression, and if we multiply voltage on both sides, it will give us the expression for the total reactive power after the power factor correction. So this is going to be the total reactive power after the power factor correction, and that is going to be equal to the lagging reactive power before power factor correction minus the leading reactive power drawn by the capacitor, or you can say that the volt ampere drawn by the capacitor, or we can say that it is going to be the reactive power supplied by the capacitor to the load. So this is how we can calculate the total reactive power after the power factor correction. So with this, I will conclude my today's lecture, and we will discuss the rest of the power factor story in the next lecture. Thank you very much.